Hello everyone. So let's continue with our lecture on the parabolic equation, the 2D case. Yes, in our last lecture we looked at an introduction to the heat equation in 2 dimensions, and then I introduced some simple schemes that we could use. We looked at the explicit scheme, the fully implicit scheme, as well as the Crank-Nicolson scheme. So these are schemes that we've seen before from our lectures on the 1D case. And then we ended our lecture by saying that, even though these simple schemes are disadvantageous, they are more restrictive, especially the explicit scheme, and the other ones, the fully implicit one, it turns out that the matrices that you get are not tridiagonal. That is why they are disadvantageous. Nevertheless, you can still use these simple schemes to do some interesting things. Like we see here that Morton and Myers use an explicit scheme to model this system, where they start off with this is the initial condition, like an M, and by time t equals 0.001, this has diffused, and then you are left with this. Okay, so that was our previous lecture. It's an exercise. So in this lecture we want to look at the approximate factorization method. All right, we are not going to dwell too much on it, but it's good we deal with this because it will continue into understanding the ADI method, which we'll talk about later on, and we'll dwell a bit more on the ADI. Okay, so let's look at the approximate factorization method. So we want to illustrate it using the Crank-Nicolson scheme that we've seen before, and I've written it here. So this is the Crank-Nicolson scheme for the 2D parabolic equation. Okay. To simplify things, we define some operators. So you let delta Uij be equal to the difference. So this difference will just be represented by this. We'll let the operator Lx represent this second order difference operator. So this one will be Lx u to the n plus 1. This will be Lx u to the n. Okay, and this one will be Ly u to the n plus 1 and Ly u to the n. So we just use this to simplify this, so that we don't carry out about this complicated expression. Okay, so we use this a lot in the subsequent lectures. So take note of these operators. So if you apply the operators to the scheme, I have just rewritten the scheme here. Then of course, as I said, this is Lx u to the n plus 1, Lx u to the n. That's this. This is Ly u to the n plus 1, Ly u to the n. So, and the top here is just delta Uij. So this is the same as that using the operators. If you rewrite this one to be this, so from this definition, equation 7, you can rewrite Uij n plus 1 to be equal to this, and then you plug it into here. Wherever we see this, we replace it with that. The equation 10 turns out to be this expression here, and of course we can combine terms. We can combine the terms with the delta u's and the terms without them, and then you get equation 11. Okay, now the delta u's are unknowns, so we have this, we have this, and we have this. So we can move the unknowns to the left hand side and the known ones, that is u to the n stuff, to be on the right hand side. If you do that, you are going to get this expression here. Okay, and then of course I can factorize delta u out, and I'm left with this expression, delta u is equal to the right hand side, which is given by this. I just move Uij(n) out of the bracket. Okay, so using the operators and using the Crank-Nicolson scheme, you get this. So we haven't really done anything. We haven't done anything about factorization. We just rewrote the Crank-Nicolson scheme in a nice compact form. Okay, that's what we've done. Now we want to, this is where we apply the so-called approximate factorization method. Okay, and there's an exercise for you to do. You note that if you expand this and rewrite the terms and put this in a matrix equation, you'll realize that the left hand side equation here is not tri-diagonal. Okay, this side is okay, we know this. This is u ij to the n, so these are known stuff. This is unknown, but the matrix that results from here is not tri-diagonal, which means it's again expensive to compute. And so the technique of approximate factorization is to factorize this such that the resulting expression on the left hand side is amenable to the Thomas algorithm. All right, so that is what we're going to do. So you're going to factorize, if you like, approximate this expression into two expressions, so that you can do some apply some processes to it. So that is approximate factorization. So what you do is this: you approximate the left hand side, which is this, to be equal to the product of these two terms. Okay, note that if you multiply these two terms out, you will get the left hand side plus an additional term, right? If you take 1 times 1, you get 1. 1 times this will give you this guy. Then this times 1 will give you that guy. These times this will give you an expression that looks like this. Okay, so it's an approximation because you are leaving out this term, but this term is second order in t. All right, so I mean, which means that we can tolerate it. The error will not be too huge. Okay, so we can leave out this term and approximate and assume that this expression here on the left hand side of the previous equation is just equal to the product of these two terms. And so now, instead of the left hand side, we're going to take this right hand side, stick it to the left hand side of the previous equation, and then boom, we have equation 14. Okay, so equation 14 is basically equation 12, I think. Yes, equation 12, but now we are replacing the left hand side here with this expression. Okay, now why is that important? Now once you do that, note what you can do. Once you do that, you can replace all of this factor here by some j, right? All of this can be replaced by something. So replace it with jij, okay, which means that the equation 14 now reduces. All of this is now jij, and then you operate it on this. You operate this on this to be equal to the left hand side, and that gives you equation 16. This equation. Okay, so you have broken it down. Now, the interesting thing is that once you've done that, the left hand side expression now is a tri-diagonal matrix. So you can solve it for jij, okay, because the right hand side is known. Once you solve this using the Thomas algorithm for jij, okay, then you go here, plug it to the right hand side. This is known. So now we can solve the equation 15 for delta u ij. Okay, and once you solve for u ij, you can use equation 7 to get the value of u then at the next time level, which is u ij n plus 1. So basically that is the method of approximate factorization. You have factorized or broken this expression down into expressions that you can use a Thomas algorithm to compute in 2 steps. Okay, so that is the method of approximate factorization. So in this exercise, all I want you, I will set it up formally, but I'll probably let you just do exercise 2A, where you would determine or demonstrate, right, using a simple stencil to show that indeed, if you leave it as this, then this matrix is not tri-diagonal. Okay, so you demonstrate that. Of course, then you can use the 2 steps to solve, but I'll just let you do this one. So that will be it for this lecture on approximate factorization. The next one that I will do will be on the ADI method, the alternating direction implicit method. Okay, so we will talk again in our next lecture. See you.